Okay, so you made it through the second test, the second section of our study in mechanics. You've looked at the empirical study of motion with kinematics. You've looked at dynamics with forces. And now we just got done with energy. All this dealing with the mechanical systems. There's another way to look at these systems, and that's through an analysis of momentum. We define momentum as the mass times the velocity of a particle. So P is momentum. It's equal to the mass times the velocity. And mass is a scalar function or scalar quantity, and velocity is a vector, so momentum is a vector. And we designate it by P. Why P? Why not? Well, it's kind of the next letter available in the alphabet. You got M is already taken by mass. You got N, which is the normal force. O is the origin of a coordinate system. And then finally you get P, and we haven't used P for anything yet. So we used it for power, but capital P. But small p, we'll use that for momentum. Probably historically it comes from the Latin word pater, which means impetus or to push forward. And so it probably comes from the Latin origins. Newton had to write in Latin. Momentum is a vector, so there are three components, x, y, and z. The momentum in the x direction is the mass times the velocity in the x direction. The momentum in the y direction is the mass times the velocity in the y direction. And the momentum in the z direction is the mass times the velocity in the z direction. Mass itself does not have x, y, z. There's no components to the mass. It's simply a scalar. And our momentum is the mass times the velocity in any respective direction. Newton called this the quantity of motion. Here's an example. Say you had a large running back moving slowly. He has some acquired momentum, his mass times his speed, his velocity, and you wish to stop him. You need to take that momentum away. So you have a smaller defensive back, maybe less mass, but maybe a greater velocity. If you can match the same amount of momentum in the opposite direction, you can make the stop, prevent them from making the first down, win the national championship. Ohio State wins. Yay! Could happen. It's been more than a decade, but we're still rejoicing in the last time that we won. Tennis ball traveling 120 miles per hour has a certain amount of momentum. Small mass with the tennis ball, but great speed, hard to stop. Baseball traveling at 90 miles per hour, a little bit more momentum because of the greater mass of the baseball. Golf ball hit off the tee. Say you were to swing, and your swing has angular momentum, and that gets transferred into the small golf ball, which will give it a great velocity, and it can go far distance then. So the angular momentum gets transferred into the linear momentum of the golf ball. All right, let's try this out. A pitcher claims he can throw a .145 kilogram baseball with as much momentum as a 3-gram bullet moving with a speed of 1.5 times 10 to the 3 meters per second. What must be the baseball speed if the pitcher's claim is valid? Well, they must have the same momentum for that to be true, and hence the mass times velocity of the bullet should equal the mass times velocity of the baseball. Hence, the velocity of the baseball we need would be equal to the momentum of the bullet divided by the mass of the baseball. We have 0.003 kilograms for the mass of the bullet over 0.145 kilograms for the mass of the baseball times 1,500 meters per second. We would need to throw the baseball at 31.0 meters per second in order for it to have as much momentum as a speeding bullet. we could test this out. 31 meters per second, convert that to miles per hour. Easy conversion from meters per second to miles per hour is to multiply by 2.2. So 31 times 2.2 will give us something around 68 miles per hour. So we could test this out. Go to the Calhoun softball fields over here. At 20 paces, you throw a ball at me at 68 miles per hour, and I'll shoot it in midair, and hopefully if they have the same momentum, they'll hit, stop, and then fall. Hopefully that would work. Or maybe you can just throw the baseball at the computer screen there, and I will shoot it, and we'll see what happens after that. What's likely is the bullet is going to have more kinetic energy. Kinetic energy is 1/2 mass times velocity squared. That's 1/2 times 0.003 kilograms times 1,500 meters per second squared, 3,375 joules, while the baseball, 1/2 mass times velocity squared for it, will give us only 69.7 joules. So what's going to happen is the bullet's going to do more damage to the baseball. It's probably going to get lodged or possibly even go all the way through the baseball. And it's going to do some damage, so all the energy needs to be dissipated either in the damage of the baseball and the bullet, and they're probably both going to heat up and dissipate energy in terms of thermal heat that way as well. So we've introduced momentum, mass times velocity. Newton's second law can actually be described in terms of momentum. The net force is equal to the infinitesimal change in momentum over the infinitesimal change in time. This is Newton's second law in momentum form. It's actually more correct than F equals ma, because in this form we can account for possibly that the mass could change. We didn't account for that before. We only assumed that the mass was constant. But in a rocket launch, you're throwing a lot of mass out, and your object is losing mass as it's being propelled in the opposite direction. So it's more correct. Note that if we did have constant mass, and we took the derivative of the momentum with respect to time, mass would come out of the derivative, and the derivative of the velocity with respect to time is indeed the acceleration. So for constant mass, this simplifies to F equals ma that we're used to, but it accounts for even a rocket situation where the mass could change. So Newton was more correct in the way he expressed it than the way we commonly use it today. Consider this. By Newton's third law, two particles may exert forces on each other equal and opposite, but if there's no external force on the system, then we can say that the system is isolated. So there's no external force on the system, only forces between the particles. Hence, we would say that the force that one exerts on two is equal to the negative of the force that two exerts on one. And if we were to add these forces vectorially, it should add up to 0 because they're equal and opposite by Newton's third law. Sounds good? So there's no net external force on this system if all the forces are internal. Now, taking Newton's second law in momentum form that we just introduced, we could write this last equation like this. Change in momentum of particle 1 with respect to time plus the change in momentum of particle 2 with respect to time equals 0. Or we can write this as the derivative with respect to time of the momentum of 1 plus the momentum of 2 equals 0. Interesting equation. But you know from calculus that if you take the derivative of something and it's equal to 0, that something must be a constant. The derivative of a constant equals 0. So we must conclude from this that the momentum of particle 1 plus the momentum of particle 2 is equal to a constant. How about that? So if we have an isolated system, no external forces, the momentum of that system will be conserved. It will be a constant at all times. Cool. We can state it like this, that the momentum we have initially of particle 1 and particle 2, P1I plus P2I, is equal to the sum of the momentum or the final momentum of the system, P1 final plus P2 final. Initial equals final. In one linear direction, we could write it like this. Mass 1, velocity 1 initial, plus mass 2, velocity 2 initial, is equal to mass 1, velocity 1 final, plus mass 2, velocity 2 final. When using this equation, these velocities could be positive or negative, depending on which direction we're going. If we define one direction as a positive direction, then anything going in the opposite direction would be a negative velocity. Because we are dealing with vectors here, and even if it's a number line, they still are vectors in a sense. So we simply have that the initial momentum is equal to the final momentum. This equation that we just showed you right here is basically your one equation to rule them all in this chapter, because we're going to be dealing with situations where momentum is conserved, and in any collision we look at, this equation will be valid. Momentum will be conserved no matter what we look at. So this is one place where you can start on almost every problem that we'll look at. Law of conservation of linear momentum. Whenever two isolated, uncharged particles interact with each other, their total momentum remains constant. As long as the acting forces are internal to the system, the momentum of the system will be conserved. Let's try it out. A baseball player uses a pitching machine to help him improve his batting average. He places the 50-kilogram machine on a frozen pond. Could happen. If you played for the Minnesota Twins and you're trying to work in the off season, you have to go outside, find a frozen pond, put the pitching machine out there. The machine fires a 0.15 kilogram baseball horizontally with the velocity of 36 meters per second. What is the recoil velocity of the machine? Alright, so we have this machine. It's got a bunch of baseballs inside, and that's the way things look like initially. And then it's going to shoot a baseball out from that way. And as the baseball goes out that way, in order to conserve momentum of the system, the machine will have to recoil in the opposite direction. Our total momentum before firing should be 0, and our total momentum beforehand should equal our total momentum afterwards. But beforehand, nothing's moving. Everything's inside the pitching machine, and it hasn't shot a baseball yet. So our total momentum of the system is indeed 0. That should equal the momentum of the baseball plus the momentum of the pitching machine. So 0 will equal mass times velocity for the baseball plus mass times velocity 2 final for the pitching machine. Solve this for the final velocity of the machine. It's going to equal final velocity of the machine, V2 final, is going to be equal to negative mass 1 over mass 2 times V1 final. Mass 1 is the baseball, mass 2 is the pitching machine. So we have a negative 0.15 kilograms for the baseball, 50 kilograms for the machine. The baseball is moving at 36 meters per second. It's probably around 80-some miles per hour. And we have the final velocity of the machine is a negative 0.11 meters per second. The negative means it's moving in the opposite direction from what we define as positive. 0.11 meters, that's about 11 centimeters, so about that far. And if it's doing it in 1 second, it's going like 1,001, 1,002, like that. So we have this machine, shoots out a baseball, boom, like that, and the machine goes 1,001 like this, in the opposite direction. What would happen if it shot out another baseball? Well, it shoots out the first baseball, boom, and it's going like this. Shoots out another baseball, boom, goes a little bit faster, almost twice as fast. Shoots out a third baseball, boom, 3 times the original speed. Keeps on picking up speed every time it shoots out a baseball in this direction. What does that remind you of? Well, the rocket situation we were talking about earlier. That's how a rocket ship works. Shoots out material at great speed in one direction, and then by Newton's third law, the momentum should be conserved for equal action. There's an equal and opposite reaction, and that propels the rocket forward and into space. So this is kind of the idea that we have going on here as well. From Newton's second law in momentum form, the net force is equal to the derivative of the momentum with respect to time. Rearrange this, our infinitesimal change in momentum is equal to the force times the infinitesimal change in time. If we integrate this from initial time to final time, we would get our change in momentum on one side and the integration as a function of time of our force. So we have on the left-hand side our final momentum minus our initial momentum. On the right-hand side, we have the integration as a function of time of our force. So we have the change in momentum is equal to this thing over here, this integral of force as a function of time. We're going to call that something. We're going to call that the impulse. So we have that the change in momentum as a vector is equal to the impulse, which is also a vector. Impulse is equal to your change in momentum. So the impulse of a force equals the change in momentum of the particle. They have the same direction. They are both vectors. Now the impulse is the integration of the force as a function of time. So anytime you integrate something as a function, you are basically finding the area underneath that curve. So if we were to graph the force as a function of time, the area underneath that graph would be our integration. And so we are looking in terms of impulse as being the area underneath this curve right here between initial and final time. This could be like a force where the baseball is hitting the bat. You know, you're swinging the bat and the baseball's coming in, and it's first not too much force on the baseball when it first contacts the bat, but then as it digs in more, the force gets greater, and then finally when it starts to reverse direction, the force starts to decrease, and then finally the baseball leaves the bat. So this kind of force curve could be something like that, where the baseball hits the bat and then comes back. We don't want to really deal with a varying force too much like this, but we do want to deal with impulse and change in momentum. So what we're going to do is we're going to select a time averaged force over the same time interval in such a way that we're going to have the same time interval, but we're going to have a constant force through that interval such that the area of this rectangle here is the same as the area of the original curve. And that would mean that the impulse delivered by our time averaged force will be the same as the original impulse of this varying force. Cool. Because if we do that, then our basic results will still be the same. So we'll have that our change in momentum is equal to this time averaged force times the change in time. Or we could say that this time average force is equal to our delta momentum over our delta time, change in momentum over change in time. So impulse equals average force times change in time. Consider these examples. A boxer moves his head backwards just before receiving a punch. If you had a fist coming towards you, you're a boxer, it's got a certain amount of mass and velocity, and it's going to be going to zero pretty quick. So there's going to be a certain exact value of change in momentum associated with that fist. It's going to go from mv to zero, and so there's a definite value of change in momentum. So there's a definite value of the impulse that's about to be delivered to your jaw. Knowing that, and knowing that impulse equals force times time, if you can increase the time of the contact, you can decrease the amount of force you're going to receive, because the product of the two is going to be at some value, no matter what. So if I can increase the time by moving my head backwards, I can decrease the force on my jaw and maybe save my jaw from being broken. So that would be the strategy, as opposed to moving my head into the punch, which would decrease the time and then probably ensure that I would break my jaw. A truck stops by colliding with a haystack instead of a brick wall. Same basic principle. If you lessen the time, you're going to greatly increase the force, hence a lot more damage on the truck in less time. If you use a haystack, then you can increase the time, decrease the amount of external force on the truck, save the truck. A car's airbag lessens the impact of a crash. Same general idea. If you're going to crash, the airbag will increase the time it takes for you to change your momentum and hence dissipate the impulse. And so the force you experience will be less, as opposed to not having an airbag and just hitting the steering wheel, where your delta T will be so small that the force you experience will be too great. A karate expert breaks a stack of boards. Karate expert, I'm no karate expert, but I would think that your objective would be to move your hand as fast as possible so that your contact time is really short. And if it's really short, you can impart a very large force at that moment and hence break the boards with that force. So it's all how you're going to manage this impulse, force times time. All right, we're going to be looking at collisions, and in particular, inelastic and elastic collisions. We're going to first look at inelastic collisions. To look at these collisions, we're going to assume something. We're going to assume an impulse approximation. We're going to assume that two particles are colliding over a very short time, just like what we were just talking about. Because they're colliding over a short time, the forces between them are going to be really large. Those forces are so large and the time is so short that the other external forces that may be present will be so small in comparison that they can be ignored. And that would isolate our system. So, our collision is happening in such a short time, these forces between them, equal and opposite, are so large that all the other external forces like gravity, normal force, friction, air friction, whatever, all those external forces are so small in comparison that they don't really matter because these forces are so large. And in essence, because of that, we have isolated our system where only the internal forces matter. And we know if the system is isolated, then momentum is conserved. So we have to have that kind of condition where we have a short enough collision in time so that it's isolated, and then we can apply conservation of momentum. We're going to assume that that's the only kind of collisions we're dealing with. So momentum can be conserved. Mechanical energy can be lost, though, in an inelastic collision. Momentum's conserved. Kinetic energy is not conserved. In a perfectly inelastic collision, the objects will actually stick together after the collision. So not only will they collide and lose energy, they'll actually stick together and assume a common final velocity. So it might look something like this. Mass 1 moving in one direction to the right. Mass 2 moving to the left. They collide. And afterwards they stick together and move with a common final velocity. Momentum still is conserved. That's our key. So we have that our momentum beforehand, mass times velocity initial for mass 1 and mass 2, that's our total momentum initially, should equal our total momentum finally, which would be the total mass times their common final velocity. So initial equals final, hence we can solve for this final velocity. That is the initial momentum of the system, mass times velocity for mass 1 and mass 2, divided by the total mass of the system. Only for a perfectly inelastic collision where things stick together. Let's try it out. An SUV versus a compact car. An SUV with a mass of 1,800 kilograms is traveling eastbound at 15 meters per second, while a compact car with a mass of 900 kilograms is traveling westbound at minus 15 meters per second. The cars collide head-on, becoming entangled. Find the speed of the entangled cars after the collision. Well, we know momentum should be conserved. So we have the SUV 15 meters per second in one direction. We have the compact car 15 meters per second in the opposite direction, so that would be a velocity of a negative 15 meters per second. We know the mass times velocity beforehand, the total momentum beforehand should equal the total momentum afterwards. We can always write this one equation to rule them all to begin with. Now in this case, they're going to stick together after the collision, so our V1 final and our V2 final will actually be the same, and so we can rewrite this as our total mass times our final velocity over here. Over on the left-hand side, we have the mass of the SUV with a velocity of 15. We have the mass of the car, 900, with a velocity of a negative 15, supplying a negative momentum. And we add those together, that should equal the final momentum of the system. Solving for a final velocity, that's going to equal 13,500 kilogram meters per second over 2,700 kilograms, 5 meters per second. So I guess the SUV1. SUV comes in, it's got more mass. Cars coming in, less mass, same speed. They collide and they end up going 5 meters per second after the collision. Might look something like this. How much kinetic energy was lost in this perfectly inelastic collision? Well, to find out how much was lost, we need to calculate how much we had to begin with, how much we end up with, and the difference between the two is how much we lost. Our initial kinetic energy, 1/2 mass times velocity squared for each mass beforehand. For the SUV, mass is 1,800 kilograms, moving at 15 meters per second, squared. For the compact car, mass is 900 kilograms, negative 15 meters per second squared. Doesn't matter as far as kinetic energy is concerned. The negative is going to square out, so it's still going to be a positive quantity for the kinetic energy of the car. This gives us 303,750 joules of kinetic energy to begin with in this system. Afterwards, they stick together, so they have a common final velocity. So we can write this as 1/2 times their total mass, 2,700 kilograms, times their final velocity, 5 meters per second squared. We end up with a final kinetic energy right after the collision of 33,750 joules. That's immediately after the collision. So due to the collision, we lost 303,750 minus 33,750, or 270,000 joules. Where did that go? Well, it went into the deformation of the cars, the friction, the deformation of the airbags, or the people inside, broken bones, whatever. Heat. The cars are going to heat up because of this collision. So all the energy is dissipated to the environment in some way or another. And momentum was conserved, but kinetic energy, the energy of motion, was not. So we lost about 89% of our kinetic energy in this collision. That concludes the first lecture in this chapter 9, dealing with momentum. We will next look at more collisions and include elastic collisions